An airplane accelerates uniformly from rest. A physicist passenger holds up a thin string of negligible mass, to which she has tied her ring, which has a mass m. She notices that as the plane accelerates down the runway, the string makes an angle theta with the vertical, as shown over here. The plane reaches a takeoff speed of 65 meters per second after accelerating for a total of 30 seconds. Determine the minimum length of the runway needed. So let's start with that. So we have a kinematic equation that says the displacement is equal to the initial velocity times the time interval plus 1/2 times the acceleration times the time interval squared. So from that, we can use this to figure out the acceleration and the time. So to figure this out, we first need to figure out the acceleration. So we know that the initial velocity of the aircraft is 0, since it starts from rest. So now we know that the displacement is equal to simply 1/2 times the acceleration times the time interval squared. So we need to figure out the acceleration. So there is another kinematic equation that says that the final velocity is equal to the initial velocity plus the acceleration times the time interval. Again, the initial velocity is equal to 0 since the plane starts from rest. So the final velocity is equal to the acceleration times the time interval. And solving for the acceleration, let's get that it is equal to the final velocity divided by the time, which is 65 meters per second divided by 30 seconds, which is about 2.17 meters per second squared. So that is the acceleration. Now all we need to do is just plug everything in to find out the displacement, or the minimum length of the runway before it takes off. And that is equal to 1/2 times acceleration, 2.17 meters per second squared, times the time interval squared, just 30 seconds squared. Now this will get you about 976.5 meters. So I'm just going to say 976.5. So for part A, the minimum length of the runway is 976.5 meters. That's the first part. Now we need to determine the angle theta that the string makes with the vertical during the acceleration of the plane before it leaves the ground. So let's draw a free body diagram quickly. If this is the ring, we have a tension force acting on it from the string, and the force of gravity, or mg, acting on it downwards. Now, this tension force can be split up into its horizontal and vertical components. Again, this is vector decomposition, and this is pretty much the exact same thing as when you decompose the initial velocity vector of a projectile that is thrown at an angle. Except this time, the angle is up here instead of down there. So instead, this horizontal component of tension will be the tension times the sine of theta, and the vertical component of the tension force will actually be t times the cosine of theta. So with this, we can set up a few equations. So first of all, if we look in the horizontal direction, we see that the only force acting on the ring in the horizontal direction is the horizontal tension force, which is given by t sine theta. And that is simply equal to the mass times the acceleration, since there are no other forces acting on it. And as for our other equation, we can say in the vertical direction that the tension times the cosine of theta minus the weight of the ring, or mg, equals ma, which we can substitute in later. And that is equal to 0, since in the vertical position it is not moving at all. So the acceleration in the vertical direction is 0. So in this case, the tension times the cosine of theta is simply equal to mg, or the weight of the ring. So now that we have these two equations, we can solve for tension so that we can substitute it. Up there. So solving for t is equal to the weight of the ring divided by the cosine of theta. So now if we plug tension in, get that the mass times the gravity divided by the cosine of theta times the sine of theta is equal to the mass times acceleration of the ring in the horizontal direction. So now we can get rid of m since they're both present, so they cancel each other out. I'm going to make some more room real quick. And then if you recognize the identity sine theta over cosine theta, you might know that equals the tangent of theta. So we can replace sine theta over cosine of theta with tangent of theta. And then we have the gravitational acceleration that we can't forget about. And that is simply equal to the acceleration. So we need to solve for theta. So you can say that the tangent of theta is equal to the acceleration divided by the gravitational acceleration. So theta is equal to the inverse tangent function of the acceleration over the gravitational acceleration. So solving for theta, can get that's the inverse tangent function of the acceleration from earlier, 2.17. Again, this is in the x direction, not in the y direction. This takeoff acceleration that we calculated was the acceleration in horizontally. The plane was not accelerating vertically, and this is why this yielded the t cosine theta minus mg is equal to 0, since there was no acceleration from the plane in the vertical direction. Just to get that clear. And then we can divide that 2.17 meters per second squared in the x direction by 9.8 meters per second squared gravitational acceleration. And this yields you about 12.5 degrees. So that is the angle theta. Oops, messed this up. So for part B, the angle theta is about 12.5 degrees. And that is how you would solve this problem here.